All right, ladies and gentlemen, welcome to the last section of chapter 6. This is some fun stuff in this section. We're going to look at complex numbers. We're going to look at using trig and combining trig with our study of complex numbers, and we're going to do some cool stuff with it. All right, so let's first look at what it means to be the trig form of a complex number. Now, a complex number is, as we recall, z. We always use the letter z for some reason in math. A plus bi, something like 2 plus 3i or 4 minus I. Those are complex numbers. Or even 3 minus 0i or 3 plus 0i. So that's like a real number in complex form. All right, so these are complex numbers. You probably remember that from last year or maybe earlier this year. And trig form is given by a very simple statement. Instead of having a plus bi, we can write this as r times the cosine of theta plus I sine of theta. Now, you're probably trying to figure out what's going on here. I is obviously I, and r you might kind of compare to everything else we've been dealing with r in this chapter. R is the length, or the, as we call it, I'm going to write this here in a minute, but the absolute value of z. And theta is just the angle at which we would say this point is at in our quadrant somewhere, on our axis somewhere. All right, we have a shorthand for this because theta is the same number and r is obviously r. We shorthand this r times the cosine of theta plus I times the sine of theta. We write it as r cis theta. So if you ever saw 3 cis 25 degrees, it means 3 times the cosine of 25 plus I times the sine of 25. So it compares like that. We can write them similarly. Either one works for me. I don't care which one you write, but obviously the CIS version is simpler. All right. So R is, as I just mentioned a second ago, this is absolute value. Or in actual math terms, this is called the modulus. We call the modulus of z the length or the distance from zero sort of thing. Okay, so it's the absolute value of z. And you find modulus, or you find absolute value, by doing the square root of a squared plus b squared, because it's distance. That's my r. So if you want to write that somewhere, r is equal to the square root of a squared plus b squared. Theta is obviously tan inverse of b over a. We've done this quite often in this class already. And we can find theta using tan inverse. And this is called the argument. So if you're ever asked, what's the argument and modulus of the complex number? It's basically asking what's the theta and what is the distance, or what is the length of that z complex number. So what I want to do here is I want to find the trig form of this complex number. So I need to find r. R is equal to the square root of 1 squared plus root 3 squared. Notice I don't really care about the negative because the negative is just going to square to become positive. Some of you should probably stop thinking about the negative because you forget to put the negative in parentheses. I get 1 plus 3, which is 4, so it's 2. So I already know that z is equal to 2 cis something. I need to know what that something is. So now I need to find theta. Theta is tan inverse of negative root 3 over 1. And if you do that on your calculator for some reason, you could get this. The tan inverse of negative square root of 3 divided by 1. I don't know why I did divide by 1, is negative 60 degrees. On your calculator, you get negative 60 degrees, and you probably should figure that out because it was actually a real, or not real, a special number, special angle. And you can leave it as a negative 60. You just got to make sure you're in the right quadrant. Negative 60 is in quadrant 4. Going right 1 and down root 3 is in quadrant 4. So negative 60 is the correct angle. And that is trig form of a complex number. Very, very simple. But we need to be able to use this in different fashions. So what we want to do is we want to be able to multiply and divide complex numbers quickly. So you might remember having to do something like this. 1 plus 3i times 1 minus 2i times 1 plus 6i. And it kind of got ridiculous after a while. Now here's where this kind of comes in handy. If you have two complex numbers, z1, which has an r and a theta for itself, and z2, which has its own r and theta, if I wanted to find the product of, or sorry, I guess I do it quotient first. If I want to find the quotient of the two complex numbers, remember this is for trig form, z1 divided by z2, all I have to do is divide the r1 by r2 and subtract the two thetas. Very, very simple. If you had to do this in longhand, you would actually have to multiply by 1 plus 3i over 1 plus 3i, and you have to do that, and then you have to do this, and this is actually a much simpler and quicker thing to do. And you might kind of guess that if I wanted to find the product of these two numbers, well, division was division and subtraction. Well, multiplication is just multiplication and addition. So if I multiplied two complex numbers together in trigonometric form, I would multiply their two modulus together, and I would add the two arguments. Very, very simple. So let's find the product and quotient of these two examples that I have here, or this one example I have here, two different complex numbers. One number is already in trig form for us. Notice the r is 25 root 2, and the theta is negative pi fourths. My second one's not, so I need to figure this one out. R is the square root of 7 squared plus 7 root 3 squared is 49, and let's see, that's 49 times 3, so brain's not working today. 49 times 3, 147. Which is 196, the square root of 196, and you might not know that, but that is the square root, or the square of 14. Well, that's good because that means r is a nice number rather than a kind of ugly number. And then I need to know theta. Theta is, tan inverse of 7 root 3 over 7. Well, that's actually just root 3, and I'm pretty sure we could figure that out from before, that instead of using a negative number, we're going to use a positive number, and we get positive 60 degrees. And that makes sense because 7 root 3 is in quadrant 1, and that's in quadrant 1. But we don't really want 60 degrees. We want pi thirds. And you might understand why we want pi thirds, because the other one had pi fourths. So if I want to find z1 times z2, I didn't write this anywhere, but I'm going to write this up here at the top here. Z2 is now the complex number 14 CIS pi thirds. And this, by the way, is 25 root 2 CIS negative pi fourths, just written in long version. All right, so if I want to find the product, I'm going to find the product of their two r values, their two arguments, or not arguments, modulus. And I'm going to add their two arguments. So I look here and I go 14 times 25 is 350. Square root of 2 times the CIS. This is actually 4 pi over 12 minus 3 pi over 12, so we get a result of pi over 12. Notice if we were to try to divide z1 by z2, that's pretty simple as well. If we did z1 over z2, that would be 14 over 25 root 2. Obviously, you'd have to simplify that. Oops, not equals. Times the CIS, not cosine, that's not what that's supposed to say, CIS of, well, this would be 4 pi 12ths plus 3 pi 12ths, so I would get 7 pi over 12. All right, so multiplication and division of complex numbers in trig form are very simple. The thing is just you might have to try to figure out what the CIS version was, but again, that's not too challenging. Now, we're going to look at something that comes from all of this here is if I was to try to do z1 to the 5th power, I would have to do z1 times z1 times z1 times z1, and you might notice that I would do r1 times r1 times r1 times r1, and then you just keep adding up the thetas for as many as you have. Well, this guy, de Moivre, got his name attached to this theorem. So it's one of those things like the Pythagorean theorem. His name just got attached to something he didn't actually invent. All right, so I'm not sure if de Moivre actually invented this or not, but I have a feeling that he might have just used it a lot. So if you were to follow that multiplication and say, okay, well, z1 times z1 is r1 times r1 and CIS of theta 1 plus theta 1. Well, let me say instead of doing, what if I didn't do just z1 squared? This is squared, right? Because it's z1 times z1. Well, if I did 3, well, then I just have to add another r1, and I'd have to add another theta 1. And notice I have 3 of these r's and 3 of these thetas. Oh, well, let's say if I went, okay, what about z to the 5th? Well, I need 5 of these r's, and I would need 5 of these thetas. Well, this gets kind of boring after a while. So what we can actually say is, if you're given a complex number in trig form, and you wanted to take the nth power of z, well, it would just end up being r to the nth times the CIS of n times theta. And it's like, wow, this guy got his name onto this little itty-bitty formula as his theorem. I'm not sure how, but this actually comes in handy for us. Like for this, 1 plus root 3i to the 3rd power. This might have been something you had to do in Algebra 2. Well, in Algebra 2, you were required to go 1 plus root 3i times 1 plus root 3i times 1 plus root 3i. And then you had to do the long process of foiling this out. With 2, it's not very bad at all. With 3, it's really not too bad. But once you get to the 4th power, 5th power, 6th power, then it gets obnoxious. That's why this is handy for us. So let's figure out what the trig form is. R is the square root of 1 squared plus root 3 squared, which is 1 plus 3, which is 4, so therefore it's 2. Theta, we figured this theta out before. It's tan inverse of root 3 over 1, so it's 60 degrees, or let's just keep in the fashion of radians of pi thirds. So that means this number is actually z equals 2 CIS pi thirds, and I want to find z to the 3rd power. Well, using this very simple formula that this guy de Moivre got his name attached to is just, okay, well, it's going to be the r to the 3rd. Okay, so it's 2 to the 3rd CIS of 3 times pi thirds. So 3 times pi thirds, which means it's 8 CIS pi. Now, what we might want to do is actually put it back, and I'm gonna ask you to do this, put it back into standard form, a plus bi. This is standard form. So what we need to do is we need to think of this as 8 times the cosine of pi plus I sine of pi. Going back to a standard form is actually very, very straightforward. What is the cosine of pi? Well, cosine of pi is, cosine of pi, let's see, -1. Okay. Plus I times the sine of pi. Well, sine of pi is 0. That means we just figured out that this is 8 times -1, which is -8, plus 0, which means the answer is -8. So we just said that 1 plus √3i to the third power, done all the way down here in trig form, comes back with an answer of -8. And I want us to think about this for a second, because where we're going next is the other direction. Thinking about what does that mean? How do these two things, how does this compare to this? Well, the cube of this is -8, which actually means the cube root of -8 is this. Well, that's kind of weird. We've never taken a cube root of -8 and gotten a complex number before. So this, to me, is one of probably the coolest things that we're going to do here, is actually taking the roots of numbers. And I always ask people, what is the square root of 1? And I hope everybody said 1, but you're not fully right. Now, some of you probably said, oh yeah, -1. Right, because there are 2 answers to this statement. Right, there are 2 numbers which make this statement true. 1 squared equals 1, and -1 squared equals 1. Okay, we know that to be true because there has to be 2 answers to a quadratic. Now, what if I was to say, what are the, pen went away. What are the cube roots of 1? Well, again, you probably should say 1. But then you're thinking, oh, Mr. just put a comma right there, which means there's another one. Well, some of you are probably going to say, oh, it's -1. But -1 to the third power is not +1, which means -1 is not an answer. But back in Algebra 2, we said in the fundamental theorem of algebra, if I gave you an equation like this, actually, if I said a 3 right here, you know that there needs to be 2 answers to this problem. Well, sometimes they're imaginary. The fundamental theorem of algebra actually says this: x cubed plus 7 equals 0. There are 3 answers to this statement. Again, something might be complex. Again, it continues to this: x to the nth power equals 0. There are n answers. Actually, not 0. I don't like 0. 0 is not what I wanted there. Let's say it's 7. X to the nth power equals 7. There are n answers to this statement. There has to be. Which likewise tells me this cube root of 1, there are 3 answers. But you're going to sit there and rack your brain trying to figure out what the answers are, because you're not going to figure them out without this thing that we're getting at. And then I'm going to ask you this: cube root of -8. Well, you can take the cube root of negative numbers, and most of you are probably going to say, oh, it's -2. But then again, Mr. just put a comma sign there, so there has to be another one. And if you didn't figure out the other one, you weren't paying attention about 2 minutes ago when we said 1 plus square root of 3i is one of the solutions. Well, then you're like, well, how do we figure that out? I'm going to show you. Well, it turns out, I'm pretty sure, I'm trying to do this off the top of my head here, 1 minus √3i is also one of the solutions. But we'll get to figure out that in a second. Here's how we're going to do it. I'm asking questions that I already had up there. Yeah, talking myself. Fundamental theorem of algebra. See, I was talking all this stuff, but I never actually put up the PowerPoint. All right. Take a deep breath. You're not going to like this next formula. Okay, if you are given a complex number in trig form, this has to be done in trig form. If you want to take the nth root of that number, first, you need to take the nth root of r. So it's really nice if r is a good number, like 1. Not always the case, though. Then it's going to be CIS of theta plus 2 pi k over n. Huh. And you're probably racking your brain going, I have no idea what's going on right now. Now, you'll notice that the r and the CIS and the theta all come from the number itself. So this one's pretty easy. This one's given. This one's given. And if you want to take the fifth root, you know this is given as well. In and in. That means it's 5. In is 5. Okay. Well, here's the thing. CIS, that's just a statement. And 2 pi, well, that's just a number. But then you're probably looking at this little k and going, what? What is that? Now, here's where k comes in. K makes it so you have to do this problem multiple times. And you have to, because if I told you to find the fifth root, guess how many times you're going to have to do this statement? You're right, 5. Well, this is for, you're looking at k equals 0, 1, 2, ... all the way up to n minus 1. So if I said take the fifth root of 1, you would do this whole formula. Obviously, you would have 1 plus 0i. You would find your r. You would find your theta. That's easy. You knew n is 5. Well, in order to solve this problem, you're going to have to do k equals 0, k equals 1, k equals 2, k equals 3, and k equals 4. Because as soon as you do 5, then you've just repeated the process over and over and over again. Okay, so don't forget this right here. This is super, super important. Everything else in this formula is given to you from the given question, and this is where the problem kind of comes into play, like the big problem. So here's what we're going to do. We are going to calculate the nth root of unity. And you're like, I have no idea what that means, mister. And I'm going to say, you're right, you probably don't. But it just means this. Square root of 1. Or sorry, the 8th root of 1. And you could probably figure out that a couple of the answers are 1 and negative 1. You're right. But how many more do there have to be? Well, I hope you said 6. Because that's only 2 of the 8 answers that are required from this particular statement. So I have the complex number 1 plus 0i. And I need to put this in trig form. Well, some of these trig forms are actually very easy, especially if you have whole numbers like this, real numbers like this. The r value is the square root of 1 squared plus 0 squared. Well, that's easy. It's just 1. Okay, so r equals 1. And theta equals. Well, you don't really have to do too much for this particular problem. If you were to graph the number 1 plus 0i, 1 plus 0i is here. Oh, well, that angle there, theta is 0. So we have r, which is 1, CIS 0. And you're like, well, that seems very simple. It kind of is. Now, we have to do this problem 6 times. If you want to list this, k has to be 0, 1, 2, 3, 4, 5, 6, and 7. So we have to do this 8 times. Ah, mister. Okay, so this is kind of how I do the problem. I just start with k equals 0, and we go from there. So we need to take the nth root of r. So here's where it gets a little funny. 8th root of r is the 8th root of 1, and what we use here is just the common root, so it's 1. So the 8th root of r is just 1 times the CIS of. You just follow the formula. Theta is 0 plus 2 pi times 0 over 8, which is CIS. If we were to simplify this, 0 plus 2 pi times 0 is 0 over 8 is 0. Okay, so CIS of 0. Notice CIS 0 is what we started with. Well, we said one of the answers is itself. Okay, so there's 1. Let's try number 2. K equals 1. All right, K equals 1. Well, this doesn't change. This doesn't change. This doesn't change. That doesn't change. Here is where it changes. And I simplify this. CIS. All right, 0 plus 2 pi over 8. Well, 2 pi over 8 is pi over 4. Ah, cool. Okay, that's pretty easy. All right, so what's the next one? We have to do K equals 2. 1 times the CIS of 0 plus 2 pi times 2 over 8 equals. Okay, so 2 pi times 2 becomes 4 pi. 4 pi over 8 is pi halves. And we get CIS of pi halves. Okay, so I'm going to get, got to change colors here. Let's go with black here. So, okay, K equals 3. Notice that this is a process. I can't do this really any faster either. In this particular case, I could because of the way symmetry works, but I'll talk about symmetry in just a second. Two pi times 3 is 6 pi over 8 is 3 pi fourths. You might notice if you're going around the circle here, here is the number that I started with. The next number is 1 unit from 0, pi fourths of a degree, or pi fourths of a radian. Pi fourths radians. Oh, that's cool. CIS, okay, so the R is still 1, and its distance, okay, there we go. And there we go. And we've only done 4. That's 3 pi fourths. Where do you suppose the next one's going to go? Well, we're going by pi fourths. The next one better be here, and then here, and then here, and then here. Now, I'm just using symmetry. I started here and broke the circle up into 8 parts, which is the 8th root, by the way. But what I want to show is what these numbers actually kind of are. Now, that's symmetry. Not everybody's going to get that right away. You can kind of play with it, and they do ask you to actually graph your answers. And that's all you're graphing is going to pi fourths, so going 1 unit out, and they should end up in a full circle. So when I divided the circle into 8 parts, each angle was 45 degrees away. If I cut the circle into 5 parts, then it would be 72 degrees away, kind of like that pentagon problem from the other day. So some of you are probably going to go, oh, can I just continue this pattern? And you can. I want you guys to be careful, though, as you go and not try to get overly clever and try to figure out all of the answers all at once. So I went by pi fourths, pi fourths, pi fourths, pi fourths. This would be 5 pi fourths. 6 pi fourths, which is 3 pi halves. And lastly, we would have, let's put this over here, CIS of, what is the next one? 7 pi fourths. Now, if you were to put these back into trig or the standard form, this would be 1 plus 0i cosine of pi fourths is root 2 over 2. And sine of pi over 4 is root 2 over 2. Pi halves, that would be 0 plus 1i. And you can verify for this for yourself if you're not quite convinced here. Just do cosine of 3 pi fourths and sine of 3 pi fourths. And so on and so forth. This would be negative 1 plus 0i. And going down the line like such. Okay. This is an 8th root, which meant you had to do the problem 8 times. So make sure you're paying attention to the problem. If I tell you to find the 8th root of 1 and you only give me 1 and negative 1, you're basically fully incorrect because you did not follow this process. All right? Be very careful thinking that everything comes out really, really nicely like mine does as well. Just because this is a whole number, a real number. Some of your problems might be saying, hey, find the cube root of 1 plus 2i. All right? There are little kind of tricks that you can kind of find in this method or in this madness, if you want to call it a madness or a method. But be careful. You got to prove it to me if you think it's a true trick. All right? So I'm going to leave you with this. I hope this, again, enlightened you. This is, like I said, the last section to the chapter. And I will see you guys tomorrow.